This is a great example of a velocity time graph and how to analyze it. So we're going to go through it. This question was on the extra practice sheets for graphing, and we're told that to consider east as being the positive direction. Let's start taking a look at it. So I'm going to just record at the right hand side what's going on here, and you can follow along. So in section A, this is a velocity time graph. So I'm thinking some people might say that that's moving at a constant velocity because the slope is constant. But this is a velocity time graph. That would be true on a position time graph. In this case, the velocity is increasing. We can see here that the velocity starts off being 0 right here. And at this point here, the velocity has increased to 25 meters per second. So it's definitely not a constant velocity. The velocity is increasing. And when the velocity is increasing at a uniform rate, as it is here, because the slope is constant, then we would say that this is constant acceleration. So constant acceleration here. And since acceleration is a vector quantity, we need to give a direction, so that would be constant acceleration east. Moving along to section B. In section B, the velocity is constant. It stays at 25 meters per second. It's still moving, has a velocity, 25 meters per second. So we would say that this is a constant velocity. And the direction is still east. In section C, very similar to section A, only this time the velocity is decreasing. It's getting closer to 0. We don't say deceleration though. We say constant acceleration east. That does not mean it's moving east. It's not. It's actually still moving west. But the acceleration is east, and if the acceleration is in the opposite direction to the velocity, then the object will be slowing down, which is the case here. In section D, now the velocity is actually increasing. It's going from 0 at 420 seconds to negative 75 at about 520 seconds. So the velocity is increasing. So we're going to say, again, it's a constant slope, so it's a constant acceleration west. But section C and section D are actually different kinds of motion. So I'm just going to slide that in here. In section C, it's a constant acceleration east, but it's moving west, so it's actually slowing down in section C. And in this next section, it's speeding up because the velocity is west and the acceleration is west in section D. Section E is moving at a constant velocity. It's not accelerating anymore, but it's still moving. It's a constant velocity of negative 75 meters per second, or in the west direction. And section EF is very similar to section D. It's moving at a constant acceleration west. And it's moving west, so it's speeding up just like section D. So there's a description of what's going on in each of those sections. So I've answered part A there. And part B now is asking me to find out, or to describe, how fast is the train moving at each of these times. Now this is how fast means velocity. So let's just take a look at that. When we see the term how fast here, how fast could mean speed or velocity. So right here, how fast, we're referring to the speed, or the velocity, I should say. And this is a velocity time graph. So all we have to do to find the velocity from a velocity time graph is just read it off the graph. So I'm going to write that in here. Read off graph. So if we look at our graph at each of the different times, So we want to know what is the velocity, for example, at 60 seconds. So I'm just going to show you how to do that, and then we'll fill it out. So if I find 60 seconds on my graph, it's right here. So if I go up to from 60 seconds up to the graph and then read across, I can see that it's about 12.5 meters per second for 12.5 meters per second east for the velocity at that time. So now all I have to do is write them in. So I'm going to do that. So let's see what we've got. Starting off with 60 seconds, the velocity is 12.5 meters per second east. And so on. So I've completed those values. Here they are. Just going to highlight them here. So we've got at 60 seconds, 240 seconds. Just want to take a look at this one. At 480 seconds, comes to negative 50 meters per second east. But that's the same as 50 meters per second west. So either of those is fine. If you just read it off the graph, you get negative 50 meters per second, and that's in the east direction. That's the same as 50 meters per second west, so you can write either. We're not too worried from graphing questions. It's kind of hard to determine the significant figures from a graph. So not too worried about significant figures in your answers from the graphing questions. Problems, of course, we definitely would think about significant figures. So, what's next? Let's scroll down and see what else we're trying to find. So next section is to find the acceleration from each of the lettered sections. The acceleration is the slope. So for each of the sections, all I got to do is find the slope, and then I can get the acceleration. So if I take a look at this first section, section A, the change in velocity, or the rise of that section, is 25 meters per second, and the run is 120 seconds. So if I do rise over run, that will tell me my acceleration. So for section A, the acceleration is slope, which is rise over run, which is the same as delta V over delta T in this case. And the rise is 25 meters per second. The run is 120 seconds. And if I divide those, I get 0.21 meters per second per second. And the direction is east. Okay, so that's it for section A. I do the same thing for the other sections, and I can write them in there. So I've completed those calculations for the acceleration in each of the sections A to F, and there they are. Again, if you look at section E, the slope is a negative slope. Looking at the graph for section, not section C, but section D. So what that means is, if you take a look at it, in section D, you can see it is a negative slope. So you can have a slope of negative 0.75 meters per second east. But that's the same as 0.75 meters per second west. That doesn't mean it's moving west, again, so it's really important to understand what does an acceleration of west mean. It depends on what the velocity is. So if the thing is moving to the west, which in this case it is, and the acceleration is to the west, then it will be speeding up. It's accelerating in the same direction as it's moving, so it's speeding up. If you contrast that to section C, in section C the acceleration is to the west, but the object is still moving to the east, so it's actually going to be slowing down in that section C. So let's move on now and take a look at the next section. How far has the train traveled in each of the lettered sections? So how far here, what we're referring to when we say how far is displacement. So you may recall, hopefully you recall, that the displacement is found from a velocity time graph by finding the area between the graph and the axis. So if I take a look at section A, and so I'm going to shade it in here. So if I find this area here between the graph and the time axis, so I've shaded it in. If I find that area, that's going to tell me the displacement. And for this particular area here, we actually have a triangle. And so the area of this little section here is base times height divided by 2. So 120 multiplied by 25 divided by 2. And that comes to be 1500 meters. And it's going to be 1500 meters east because it's above the time axis. Now I'm going to do that for the other sections. I'll show it on here, what I'm shading and my calculations, and then we'll go from there. So recall that I am always finding the area between the velocity axis and the velocity graph and the time axis, and that any displacements that are above the time axis are east, such as in section C, 1500 meters east, and in the last section, 12,900 meters west. And I'm always going all the way to the time axis. The last part of the question is to take a look at what is the total displacement. So to find the total displacement, all I have to do is add up the individual displacements, A plus B plus all of the different sections. And if we look at that, we've got positive 1500 meters for section A, plus 4500 meters for section B, plus 1500 meters for section C. And then we've got negatives, so negative 3750 meters, and then negative 6000 meters, and negative 12,900 meters. And if we add all of those numbers together, we get, I'm just going to put it up here, we get negative 15,150 meters, or 15 kilometers west. For our total displacement. So in summary then, what we see is from a velocity time graph, there are three things we can find. We can find the velocity at a point just by reading it off the graph. We can find the acceleration by finding the slope of the graph. We can find the displacement by finding the area between the graph and the axis. One last thing we could find is we could find the average velocity for the entire trip. And the way we would do that is we wouldn't average together any velocities because the time intervals for each section are quite different and the type of motion in each section is different. But what we can do is we can take the displacement for the whole trip, or any part of the trip, but let's think of the whole trip, so there are 15 kilometers, and if we divided that by 720 seconds, then we could get the average velocity for the entire trip. So lots of things you can find from a velocity time graph.